All right. So last time we introduced the thing which is called a capacitor, right? So the role of a capacitor is to like store charge, and in a sense, it's also store energy. So I will remind you again what we did last time. So last time we talked about a capacitor, which is kind of like most kind of like simple way of building a capacitor, which is just taking a parallel plate. Parallel plate mean one plate and the other one kind of in parallel, almost touching like this, right? So they can be the same material or different material. It doesn't really matter. It just have to be conductor sheet, really large, and the gap between the two, let's say, is given by D. Okay, and the area is A. So the top, which is in red, has the area A, and the bottom will also have an area A. Okay, and to use a capacitor, you need to usually charge the capacitor up, and by charging, you have to kind of connect a capacitor to usually like a battery or like a power source, but the battery is probably more um, kind of familiar to you. So you can connect. So you take a battery, and then you can connect the top plate to the positive terminal, and then the bottom plate to the negative terminal. So the battery will have what we call a potential difference, delta V, between the positive and negative terminal to be, given by delta V here. And for example, this can be 1.5 volt or 12 volt if you use, car battery. It doesn't matter, but the thing which is important is that delta V is given to you by the type of the battery. So you know the number exactly. Okay, but what's exactly the number? That depends on the type of the battery. So just not write that because we want to be a little bit more generic here. So the role of the battery is to draw electron from the top plate and then put electron to the bottom plate like this. Okay, so this process which involve electron moving will just go on until in the end the potential difference between the top plate and the bottom plate is equal to the potential difference of the battery, right? So at some point the top plate and the bottom plate will have the potential difference of delta V. And when that happens, this potential difference is the same as that, right? So if you have the potential to be the same, then charge will stop flowing because it doesn't help anymore by moving the charge, right? Remember that we want to lower the potential energy as much as we can, right? So if the thing that you do or the thing that the system does not really lower the potential energy of the system, then there's no use of doing that thing, right? So that thing might or might not happen. Usually it doesn't happen, right? So in the end, the potential difference between the top and bottom plate, which is delta V, is equal to the potential difference of the battery. Then we say the capacitor is fully charged. So charge, like electrons, stop moving. Okay, and it's fully charged in the end means that there's gonna be positive charge Q on the top plate and negative charge Q on the bottom plate like this. So we found out that the amount of charge appearing on the top plate, big Q, depends on mainly two things. The thing which is called a capacitance, which again depends on the geometrical configuration of the system, like how large the plate is, the distance between the plate, okay, and of course times the potential difference of the battery that you put in, right? So this dependence on delta V is kind of makes sense because if you put more potential, let's say you use larger battery, connect to the same capacitor, you should have more charge on the capacitor, right? So Q is proportional to delta V. That's totally makes sense, I think. And C here again, it depends on how you set up the capacitor. In this particular case, so I say for parallel plate capacitor, which is um, capacitor built like this. There are many ways of building capacitor. This is just happen to be the easiest way. Okay, so for parallel plate capacitor, C is given by A, the area of the plate, times epsilon 0, the permittivity, a constant, so it's just a number, divided by D, which is the distance between the two plate. Okay, so if you have larger plate, larger area of capacitor, you have more capacitance. Okay, or if you have the same area but you move the two plate closer to each other, as close as you can but not touching, then you also gonna have larger capacitance for that capacitor. Okay, and C has a unit of farad, which we call F. Okay, after Michael Faraday, and most of the time, the capacitance that you're gonna encounter in electrical circuit, it's gonna be way less than 1 farad. So you're gonna have microfarad, nanofarad, picofarad, or something like that. So once the capacitor is charged, you can disconnect the battery, and the charge ideally will just stay on the plate because it has nowhere to go. So it's gonna have plus Q minus Q like this, and the potential difference will also stay because it's the same configuration as the one on top, right? So this is a fully charged capacitor, and then you can use this to supply some current to other things, which we're gonna talk about. I think not in this lecture, but in next lecture, the what we call RC circuit. But anyway, because you store charge and you have some potential difference between the plate, in a sense, you are storing energy in this capacitor. And without showing the proof, if you're interested, you can look at any textbook that shows the proof. So the energy stored in a capacitor is given by 1/2 times C times the potential difference squared, like this. And then you can have, like this formula entering this one to have it in different form. For example, you can rewrite this and say this is 1/2 times Q delta V square. Wait, sorry. 1/2 times Q delta V. Like this also, it also works, right? So I'm just using this one and use C equal to Q over delta V, so you can also do it like this. Okay, so there are many ways of writing this one. But in any case, you're gonna have the energy stored in capacitor in the unit of joules. Okay, so you can say, okay, I have this much energy stored in this capacitor, something like that. All right. Um, One thing that we didn't talk about last time, and is, well, it's a little bit technical, but it's good to know. So that's why we are talking about it here. Is that usually when you build a capacitor like this, um, the capacitance usually is very small. Last time we calculate briefly, 10 by 10 centimeter square sheet, and then 1 meter apart. Then you saw that the capacitance is actually in the range of nanometers, which is not nanometers, nanofarad, which is very small. And to increase the capacitance to the value that we want is actually quite difficult if we relying on like the size of the area or the like the distance d. So we have to think about other way to increase the capacitance in a capacitor, because in some application we really want to have um, large capacitance. So this is when a thing called dielectric comes in. I want to use different color. So dielectric. So what is a dielectric? Dielectric is an insulator. Okay, so electrons cannot flow freely in a dielectric because it's an insulator, but it's not purely insulator in the sense that there's no movement of the charge at all in dielectric. That's not really the case. It allows some movement of the charge. So it has something like this. So let's say I have a sheet of dielectric here. Um, it's not an it's not a conductor, so you probably can guess that it's probably not metal. But inside this dielectric, we have a lot of molecules, which looks like what we call a dipole. A dipole is a molecule where positive charge and negative charge are at the different end. Dipole. And the reason why we call dielectric is because it's a material which consists of many dipoles like this. So you have a lot of them, plus, minus, and let's say in normal configuration, these dipole will orient in a totally random way. So it's kind of like a grain of rice or something like that, which randomly oriented in this material, but it can only rotate. It cannot move. Okay, so this thing cannot move around, but it can rotate. So the best it can do is just to move positive charge to the other side and negative charge to the other side by means of rotating the dipole. Okay, but the dipole itself is not allowed to move around, because otherwise it will be a conductor, which we know is not. Okay, so we say dipole here can rotate but not move. Okay, so it's kind of like a very strange material, but it turns out that many kinds of material that we see in nature actually have this kind of property. Um, some will have a lot of dipole that you can rotate. Some will have a little bit less. In any case, what's good about this, like many dipoles in dielectric? Well, the thing is that if you put some electric field in this dipole, for example, if you put electric field everywhere from top to bottom like this, so uniform electric field, okay, so this dipole will orient themselves along the line of the electric field. So it will be like this. So the dipole, which used to be randomly oriented, now because of the presence of electric field, will orient vertically like this, and the positive side pointing down. And this is because the positive side is pushed by the electric force because of the electric field. And the negative side is pushed in the opposite direction, right, because it's negative charge, and it's going to be pushed up, right? So in the end, the electric dipole in dielectric will orient themselves like this. Okay, so and this is the crucial point. So when you have something like this, you can see that the positive negative side of each dipole will mostly cancel out because you're going to have plus and minus close to each other, except at the edge, right? Because at the edge, there's going to be the last dipole at the edge of the material, which is oriented this way, minus and plus, right? So the plus inside the material will get cancelled out by the other minus of the dipole, which is, like next to it, like this. But the minus side of the topmost dipole will have nothing to cancel out. And that's also true for the dipole at the bottommost of this dielectric. You're gonna have positive side of this dipole right at the edge of the dielectric, and it's not gonna get cancelled out. So while everything inside this dielectric is cancelled out, like equal, plus, and minus, right? But at the edge, there's no cancellation. So the effect of this looks like the dielectric develops minus charge at the top layer and positive charge at the bottom layer when we apply some electric field into this material. And you might say, okay, well, this is fine, but there's nothing special, right? Because if you take any material and then you put in some electric field, right? And then you know that electric field gonna push positive charge down because force will go down, and will push negative charge up because force will go up, right? Remember F equal to Q times E. Then it's only natural to have negative charge at the top and positive charge at the bottom. So what's so special about dielectric? Well, the special thing about dielectric is that the configuration of negative charge at the top and positive charge at the bottom, it doesn't involve movement of the charge. It only involves the rotation of all the dipoles in the dielectric. So in other words, it can do this while staying an insulator. It doesn't have to be a conductor to have this, right? If you have a conductor, yeah, sure, you're gonna have something like this because charge can move around, so there's no problem. But this is an insulator, this is a dielectric, right? It kind of like have this behavior of, like separating the charge, even though it's not a conductor. It does that by rotating a lot of dipole in the material itself. Okay, so that's kind of like the very important thing, and we want this to be an insulator for a reason that you're gonna see in a moment, right? So it's very crucial that it's an insulator. All right, so how do we use this? Well, to use this, you can actually just insert this material between the two power plate in a capacitor. So maybe I should go to the next page. I'll go to the next page. So consider a capacitor again, where we don't have anything in between. So between is air. Later on, we're gonna put some dielectric in here. Okay, but now we are not doing that. So let's say we put some potential difference between the top and bottom. Um, essentially we are trying to charge the capacitor, charge up the capacitor. So you're gonna have plus Q here and minus Q here. And remember, when this happens, it means you're gonna have electric field pointing from top to bottom like this. Okay? Remember, we also know that E is equal to delta V divided by the distance D, which is the distance between the plate. Okay? So we know that there has to be some electric field between the two plates. All right. So now what happened when we put in the parallel plate of not we put in a dielectric between the parallel plate capacitor. Okay, so the electric field will stay there, but I will draw only one of them because otherwise it's too crowded. So now I insert our dielectric, which is in blue here, and you can see now that why this is important, that is an insulator but not a conductor, because if you have a conductor, then charge here will just jump back down and then you lose all the charge stored in the capacitor, right? So the thing that you insert between the capacitor, it has to be an insulator, otherwise you destroyed the an ability to store charge. So you don't have a capacitor anymore. Okay, so a dielectric has to be an insulator in order to work. All right, so we have this electric field which is there even if when we even before we put in the dielectric. So I would say this is the electric field from the plate. Okay, from this pair of charge plus Q and minus Q. And going back a moment, when you have electric field, you develop the charge at the edge of the dielectric like this. Okay, so when you have something like this, what's gonna happen is that at the edge of the dielectric, you're gonna develop some positive charge. Okay, this positive charge is not the charge on this plate because they are not the same thing. They are not the same material. Okay, but it's in this blue thing. And on the other side, you're gonna have a lot of negative charge on the dielectric at the edge of the dielectric like this. Okay. So then what happened? Well, because you have positive and negative charge on the dielectric itself, this charge on the dielectric will also create some electric field. And electric field is going to point top to bottom. So it's going to point this way. So this electric field is E from dielectric, which point in the opposite direction as the plate. So the net effect of the dielectric, well, because before you have electric field from the plate, which is from these two charges, and then you develop another electric field from the dielectric inside this dielectric. So the total electric field inside this capacitor, meaning that between the plate, E total between the plate, you have to add the two together. So you have to add E plate, which is what you used to have before you put in dielectric, plus E of the dielectric, which is E field, developed from the separation of this positive and negative charge of the dielectric itself, like this. Okay, so even though you add them, E dielectric point in the opposite direction as E plate. So the net effect is you lower the strength of E total, okay, because they point in the opposite direction. So I can write E total, the strength of the electric field, okay, E total is actually less than the electric field before you put in the dielectric, less than that. So what happened in the end? Well, when you put in the dielectric, a few things happen. First, the dielectric lower E field between the plate. Okay, that means the dielectric lower E field between the plate according to this, right? Because E total is actually less than E plate. So E plate is the, again, electric field before you put in the dielectric. So when you put in the dielectric, you make the electric field between the plate to be lower. Once the electric field is lower, that means delta V between the plate is also lower. Why? Because delta V is equal to E times D according to this equation. Okay, so when you put in dielectric, you lower the electric field between the plate, but you don't change anything about the distance between the plates. So the effect is also you are lowering the potential difference between the top and bottom plate. Okay, so that means the potential difference on between the plate is now lower than the potential difference between the battery. So more charge can flow in. So more charge can flow into the capacitor. And what this means we have more capacitance. Okay, so it's a little bit, complicated in a sense that how these things, like leads to the other one, right? But again, what you do is that you put in dielectric between capacitor. By doing so, you lower the electric field between the plate. And that means you lower the potential difference between the top and bottom plate, right? So the capacitor, which used to be fully charged because the potential is the same as the potential of the battery that you put in, now that's no longer the case, right? Because the potential of the plate is lower. right? So it's less than the battery now because you insert the dielectric. So charge can flow more into the plate, right? So in other words, you allow more charge to flow into the capacitor without changing the battery, right? So what you do is you just insert the dielectric. So that means by inserting the dielectric, you are actually making the capacitor to have more capacitance. And the capacitance in this case is given by the same formula that we had before, epsilon 0 times A, the area, divided by the distance. But now you're going to have this extra factor here. This is called the dielectric constant, which depends on the material. Okay, so if you insert a dielectric which has large value of dielectric constant, then you're gonna have a lot more capacitance in this case, right? So what kind of material um, give you, like what dielectric constant? You have to look into the table, and this you need to go back to last lecture. In the last page, lecture 18, in the last page, you're gonna have this table which is a bunch of material with this dielectric constant K, and you're gonna see that air is very close to 1. This should remind you of something. If you remember, we talked about index of refraction before midterm. So it turns out that the dielectric constant is kind of very closely related to index of refraction. Not exactly the same, but very similar. So air is very close to 1. And if you have some different material, you can actually make the capacitor to have a lot more capacitance by just inserting, for example, this thing, strontium titanate. You can use this, you can insert this thing between the parallel plate capacitor, and magically suddenly you have like 200 times more capacitance in this way. Okay, so this is how most modern capacitors are made. There's not just two parallel plate with air between, because that's gonna give you way less capacitance that you can make. So most of the time you're gonna have some kind of dielectric in between. Okay, so that's the thing about this dielectric thing. So again, the effect of this is just to increase the capacitance. So if you are confused about like how actually the dielectric works, don't worry too much. The only thing that at least I want you to know is that if you put in dielectric in the capacitor, then it will increase the capacitance according to this value of K. That's kind of like the bare minimum thing that I want you to understand here. Okay, but how it works is what I just said here. Okay, so that's kind of the end of the intro to the capacitor. We're gonna talk about capacitor again in the RC circuit, which is probably next time. But at this point, I want to switch to discussion of current. Okay, so it's gonna be another topic here. So let me do that. So the first thing I want to talk about in this topic is the concept of drift velocity. Um, so far we are kind of talk about like electrons or charges, which is not really moving much, right? Even if we talk about a capacitor, when it's charging, then you have movement of the electrons, but usually we are interested in at the end when nothing moves. So this is what we call like electrostatic if you look at more advanced text. Electrostatics is the configuration of charge where you don't involve movement of charge. But in real life, that's not so useful because when you use, electrical equipment, you plug in to the outlet in the wall, you have a lot of movement of the charge, right? So we need to study that kind of things. Otherwise, you're missing out probably like 90% of the application of electrical, um, you know, current or electrical circuit that we use in everyday life. So what is the current? So current is essentially just movement of electric charges. Okay. Um, the the definition of current is actually quite simple, but we want to be quite careful in writing it down. So I will do it like this. So let's imagine that we have, kind of cylindrical wire of some kind of metal or any conductor, right? So like this. So a rod of you know metal. So for example, it can be copper, Cu, and normally when you talk about metal, we think about a lot of electrons inside this metal. And electron is very mobile because it's very light. Remember the mass of the electron is, like 10 to the power of minus 31 kilograms. So it's very, very light. And it can move around freely. So even if you don't do anything to this material, electron will just move around randomly because it has some kind of thermal energy similar to air molecules in gas that we talk about right at the beginning of this class, right? It is not kind of like standing still. It has to move around because this thing is not at absolute zero temperature. It has some temperature. So when you have temperature, the molecule, in this case, electrons will just move around because it has to have some kinetic energy, right? But the thing is that it moves in a totally random direction. So when you average the velocity of all the electrons in this material, you're going to get zero. Okay, so average velocity, okay, not speed. Okay, we are talking about velocity, so you need to think about the direction also. So the average velocity has to be zero because it's just random. So we can kind of make the average velocity to be not zero. And how do we do that? Well, you can put in an electric field inside this material. So you can put electric field that point this way, like this. So what happened to the electrons when you put in electric field? Well, suddenly it feel electric force, right? According to F equal to Q times E, and electrons is negative charge. So the force will point to the right. So for example, this electron will experience some kind of force to the right hand side, opposite of the electric field because of the charge being negative. Okay, so electron will try to move to the right, obviously, because there's a force to the right. But the thing is that electrons inside this material, even though it can move freely, it's not empty space. You're gonna have a lot of other electrons And even worse, you're gonna have a lot of other nucleus of the copper itself in a way. So it's not like nothing in, like nothing in along the way of the movement. So electron is gonna fly to the right. It's not gonna be like that because it's not empty space. So when electron get pushed to the right, when it moves to the right a little bit, so I'm gonna draw it here. So when the electron get pushed to the right, move to the right a little bit, it's gonna collide with something else, like other electrons, or some kind of nucleus, some other atoms, and then it can bounce around, and then it might hit another one. But the thing is that we always push the electron to the right. So even though the movement of electron might look kind of random, but if you wait long enough, then the average of the electron position will move to the right. But if you don't put any electric field inside this material, electrons still move randomly, but the movement of the electron in that case will be random such that on average is back to the original position like this. Okay, so I don't know with this might be a really bad way of drawing, but I hope you see what I'm trying to say. So this is the initial point here, this is the final point here, right? So you have the average movement to the right, so some kind of displacement to the right, when E is not zero. But if you don't have any electric field, then the average is zero displacement when E is zero, okay? But electron is moving all the time. So what's the average displacement it can move? It depends on what we call the drift velocity. So this thing will give you what we call drift velocity. Drift velocity is Vd equal to average displacement divided by time. And the only thing which is very, very important and you need to know is that the drift velocity of the electron is not the velocity of the electron itself. What I mean is this. When you have no electric field, like in this case, electric field is zero, the average displacement of the electron is zero because it moves randomly and in the end it's just like not moving, right? Because it go to the right and then go to the left and then go up and then go down. So on average, the electron is not moving at all. So the drift velocity of the electron in this case is zero. Okay, so I can write in this case Vd equal to zero because on average you have no movement of the electrons. But that doesn't mean the electron itself has zero velocity because electron will just move randomly anyway, right? So we're not talking about that velocity. So that's the meaning of the drift velocity, okay? Vd here. And the thing is that we actually saw from experiment is that if you put stronger electric field, you're gonna have more drift velocity. And that kind of makes sense because you're pushing it, stronger. Because more electric field means larger force, right? So what we can say about this? Well, let's now not worry about like the tiny movement, the random movement of the electrons. Let's say that we think about only the drift velocity of the electron. So I can write another diagram or draw another diagram that looks like this. But now I'm gonna draw only the drift velocity of the electron. So that means if I put in the electric field to the left like this, the electrons inside this material will move to the right, all of them at the same velocity given by Vd, the drift velocity. And again, this is the wrong picture, right? Because in reality, electron will just move around randomly like this, right? But we don't care about the random movement anymore. We only care about, the average displacement you get from the drift velocity. So effectively, it looks like electron is just, moving to the right altogether kind of nicely, even though in reality it's not the case. Okay, so effectively it's doing like this. Okay, so um, now we want to talk about the current. The current is, so what is the current? The current, which usually use the letter I, is how much charge you have divided by time. And you have to be a little bit careful here because like, okay, what do you mean exactly by delta Q over delta T? So what we mean is this. So you take, a cross-section area of a certain material. So cross-section A. And then you just count how much charge that go across this cross-section. That's gonna be your delta Q. Okay, so if you don't have any movement of the charge, there's no charge crossing this area, crossing this cross-section area, then delta Q is gonna be 0. So you're gonna see that how much charge you have across that area divided by time, that's gonna be the current. Okay, so the current is just the flow of the charge, electric charge, across a certain, like cross section of the material divided by time. Okay, in this particular case, we can actually calculate the current with a little bit more kind of like precision. So, if the electron is going to the right on average with drift velocity Vd, okay, so at time delta t, the volume kind of like spanned by this velocity is given by this chunk of volume. So imagine kind of like a tiny section on the wire with the length given by Vd times delta t, right? Because we are interested in, the volume, spanned by this electrons which has drift velocity Vd in the time delta t, right? So the length that we are interested in is Vd times delta t, and the volume is just length times, um, you know, the cross section area A. Okay, so in time delta t, okay, the amount of charge delta Q going across this area is all the charge contained in this volume here is given by delta Q equal to the volume of, so this is big V, not potential, this one, this is volume. So this is volume times N, which is the charge density, essentially the number of electrons per volume. Okay, so delta V times N give you how many electrons going across that cross section in 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 the time delta t. And well, we want delta q, right? So you need to multiply by the electron charge e, like this. Okay, so think about this, and you will see that it makes a lot of sense that we want to count how how many electrons going across this volume, this area per unit time. So the amount of material or the amount of electrons going across this per unit time is all the electrons contained in this volume here. Okay, so this thing is delta V, this thing, this is delta V, which is the volume. Okay, so we know the number of electrons. So how much charge? Well, just multiply by the charge of each electron, which is E here. Okay, so this is delta Q. But again, volume can be written in terms of the cross-section area times the drift velocity times the time. Okay, this is delta V written in a different way. And then N and E has to follow, right? So the current I is just delta Q divided by delta T. That's going to be equal to A times VD times N times E, like this. So this is the current. This is the relation that gives you the relationship between current and drift velocity relation. Okay. In other words, if you have the problem that asks you something like, okay, the current is this much. Well, by the way, current use the unit of ampere, named after another physicist, Ampere, and the abbreviation is A. Okay, so you're gonna get something like, okay, the current is 10 amps or something like that. How fast the electron is moving, so you can calculate V from this. Okay, so in one of your homework questions, you're gonna be calculating briefly this kind of thing. Okay, so I will stop here and then give you a 10-minute break, and then we gonna come back and continue talking about this. Okay, so I will see you in 10 minutes.